Hello students, welcome to the world of chemistry. This is Dr. Vikram Banchal and I am dealing with thermodynamics, and this is lecture number 31. In this lecture I will explain you what is the efficiency of Carnot cycle. Okay, so see, total work done W is equal to 2.303 R T1 minus T2, where T1 is greater than T2, log V2 upon V1, where V2 is greater than V1. Okay, and the heat absorbed at temperature T1, that is Q1, is equal to 2.303 RT1 log V2 upon V1 according to Carnot cycle. Now divide both above equations. So we will get W upon Q1 is equal to T1 minus T2 upon T1, and this is called thermodynamics efficiency. Okay, so this is known as T1 minus T2 upon T1 is called thermodynamic efficiency. Thus, the larger temperature difference between high and low temperature, or between T1 and T2 of reservoir, the more heat converted into work by the heat engine. So efficiency depends on difference between T1 and T2. So since T1 minus T2 upon T1 will be always less than 1, it follows that work is also less than heat absorbed. Okay, so this means that only a part of heat absorbed by the system at higher temperature is transferred into work. The rest of heat is given out to surrounding. So the efficiency of heat engine is always less than 1. So we can say that it is impossible to convert heat into work without compensation. So basically heat efficiency or heat engine's efficiency or Carnot cycle's efficiency is T1 minus T2 or higher temperature minus lower temperature upon higher temperature. Okay, so this way you have to remember. Now we will take numericals based on Carnot cycle. So the first numerical, a Carnot cycle or Carnot engine work between 500 Kelvin and 300 Kelvin, absorbs 1000 calorie from the 500 Kelvin reservoir. So from 500 Kelvin reservoir per cycle. Calculate the efficiency of heat engine and given heat rejected at 300 Kelvin reservoir and work done per cycle. Okay, what you are given T1 which is 500 Kelvin, T2 which is 300 Kelvin, and efficiency eta is equal to T1 minus T2 upon T1, which is 500 minus 300 upon 500. Okay, so efficiency will be 2 by 5 or it is 0.4. Now work done is equal to heat absorbed multiplied by efficiency, because efficiency is equal to W upon heat. That's why we can write this way. So if heat absorbed is 1000 calorie and efficiency is 0.4, then work done will be 1000 into 0.4, which is 400 calorie. Next is heat absorbed, that we have to find out. Heat rejected, which is in sync. So heat rejected will be, see, total heat absorbed is 1000, efficiency is 400. So heat rejected is 600 calorie. This is wastage. Okay. So this way we can calculate numerical. Now next numerical is the boiling point of water at a pressure of 50 atmosphere is 265 degrees Celsius. Compare the theoretical efficiency of a steam engine operating between the boiling point of water at first 1 atmosphere, second 50 atmosphere, assuming the temperature of the sink to be 35 degrees Celsius in each case. Okay, so now let us take the first one at 1 atmospheric pressure. Here, higher temperature is T1, which is boiling point of water, and that is 100 degrees Celsius, which is 373 Kelvin. Lower temperature T2 is temperature of sink given, which is 35 degrees Celsius, and it is 308 Kelvin. So efficiency eta is equal to T1 minus T2 upon T1, which is 373 minus 308 upon 373. This you have to find out. Now for second one, at 50 atmospheric pressure, well, higher temperature T1 is again boiling point of water, so which is 265 degrees Celsius given, and that is 538 Kelvin, and sink temperature of sink, which is 35 degrees Celsius, and it is 308 Kelvin. Okay, so again efficiency eta is equal to T1 minus T2 upon T1, and that is 538 minus 308 upon 538. Okay, so this way you can calculate efficiency at different temperature. Okay, that's it in this lecture. Thank you so much.